Today we will talk about ScatterPlots visualizations. So ScatterPlots allows us to plot our data objects into space, two-dimensional space, where we have the x and y coordinates system. We have already seen this in the previous first and second lecture. By taking the x and y coordinate values from our data table, we can map the data objects as points into a two-dimensional space. On the x coordinate, we will map the first attribute values or the properties that the object has for the first attribute. And the second, on the y coordinate, we will map the values for the second attribute or property that our object has. So imagine we have a table. On the rows they are our objects, and on the columns we have two attributes. They can be A and B. They can be, for example, age and height. They could be education and income. They could be patient medical exam 1, medical exam 2, whatever in the world they are. We will take their values and plot them onto the coordinate system. Wherever the point ends up, that's based on its values for those two attributes. That's where it's going to be in the coordinate system. So here we have the x and y, and here the red ones are the points. Let's take this point right here. For the x coordinate, it has, if each square represents 1, let's say here is 0, 1, 2, 3, 4, 5, 6. If each square represents one unit or one number, then this point right here is 0.5 value for x. For y, it has 0, 1, 2, 3. So this point right here, the first point, has values let me see if I can write this in here. Oh, okay. The first point has values 0.5 for x and 3 for y. So that is how these data points are mapped. Here we have x. And we have already seen this in our first lecture. So according to the attribute values from our data table, we're going to map the points into space. let me see here. So this right here is for the first point. I'm just trying to make sure that we know that this is for this point right here. Let's put this on the new line. Okay, let me just write down that the numbers here. One, two, three, 4, 5, 6. The numbers for x. That is how we get that this point right here is at 0.5, and the same for y. Okay, so that is how this point got over here. In terms of a correlation, that is, what are the points doing, in what direction they're moving. If the x-coordinates and the y-coordinates on the visualization appear to be moving upwards, this means they are increasing, then we have a positive correlation. This means that as x increases, y increases as well, and because of that, they influence each other. That is, when the one rises, it makes the other one rise as well. So this is called a positive correlation. So if we look at an age of a child and the height of the child, to give some real life example, then we find that as the child gets bigger, the child gets taller. That means when the child is growing, it becomes taller in height. Because both of those are moving upwards, the age is increasing and the height is increasing. Therefore, we have a positive correlation. The negative correlation will be the other way around. If the x-coordinates and the y-coordinates both have, this means one of them is increasing and the other one is decreasing, then we have a negative correlation. This means that when the x increases, the y decreases. This means they are related, but they're opposites. So overall, the points appear to be moving downwards in this visualization. To see a real-life example, the age of a car and its value. When the car gets older, the car costs less. This means the one parameter or one attribute value, the age of the car, is increasing, but the value of the car is decreasing. So this is a negative correlation. And then we have another example where we have no correlation. This means the values of the x-coordinate are not affecting the values of the y-coordinate. There seems to be no pattern onto this visualization as to where the points moving into some particular direction. The points look scattered and there is no correlation. So there is no relationship between the x and the y. To see a real-life example, if we look at the size of the shoe, a player wears and their batting average, we will find that the shoe size does not make the player better or worse, which means these two are not related. So let's look at the scatter plots on these visualizations here. We would like to find over here which scatter plot has a linear trend? So what do you think? Which of those would have a linear trend? Does the first one have a linear trend? Not really. That first one looks like those points over here that are scattered all over the place, and they don't look like they have any correlation or relationship, one affecting the other. Now the second one, we do have the downward trend. Points appear to be moving downward. We could draw a line between them. All of them would be near the line. So there is a linear trend and it is going downwards. We have a negative correlation. On the second one, on the third one, we have a again linear trend. Points can be aligned to a line which appears to be moving upwards, so we have a positive correlation. On the number B, again there is no linear trend, but all the points appear to be in the lower left corner, which means they have values that are small or close to 0. We will have maximum values of 1 or 2 on both the x and y coordinates if we assume the values of the coordinates are like this: 1 2 3 4 5, 1 2 3 4 5. Most of the points appear in the lower left corner, which means their values are close to 0 or their maximum value is 1 or 2. So on the fifth example here, number D, we have points that appear to be in a circle, kind of like the clusters we have seen, which have a round shape. There is no linear trend here. On the last one, we do have a linear trend. It's neither positive nor negative. It's called a constant correlation, as the points appear to be moving horizontally in a straight line, neither upwards nor downwards. They are flat. So this is called a constant correlation. Over here, we would like to plot the data points in the coordinate plane and interpret the scatter plot that we obtain. Just like we have seen here, as I explained over here, this point is positioned in exactly in this location because the value for its value for x is 0.5, which means it's right here. And drawing a straight line from here up, it ends up in position 0.5 for x. For y, it has 3. 1 2 3, so that's why it is plotted exactly here into the two-dimensional space. We're gonna do the same thing in order to build scatter plot from this data right here. We have two attributes, the year and the sales. The year is for the first point. The year is 1991. And the sales is 0.9. So that's why the first point is exactly here, as it has values of 1991 and 0.9. X is equal to 1991 and y is equal to 0.9, and that is why this point is in the location in this exact location. So the green ones are the y coordinate values, and the pink ones are the x coordinate values. See to get to the y command. Okay, so that's why the first point is in the location that it is. So let's don't remember how I got this circle over here. Let me just copy this circle. So that is why this point appears over here. Alright, so how about this point? Why is this point right here? Because it has 19924 for x and 1.1 for y. Should this need to move down? How about this one? Why is it here? Because it has 1993 for x and a 1.4 for y. And so on, the remaining points are plotted based on their values of their attributes. So this one is going to be our x. Attribute, and the other one is the y attribute. Alright, so let's analyze this scatter plot. Interpret the scatter plot. What do we have here? Is there a trend? Is the x affecting the y? Yes, it appears there is a linear trend. If we draw a line, all the points are aligned with the line, and we can see arrow pointing upwards. They appear to be moving up. This means when the year increases, the SUV cells are increasing, so there is a positive correlation between those two attribute values. Let's do some exercises here. Can you think about this and plot the data below on a graph with x and y axis? These will be our objects 1, 2, 3, 4, 5, 6, 7. They're going to be 7 points into our scatter plot, and z is here would be the x and y coordinates. So the first thing is the object number. And there we have the x is here and y is here. So for the first object, let's say this is object number 1. It has 30, value of 30 for the x coordinates. That's object number 2. The third one is Lara. She has values 120 and 30 minutes. Object number 4 is Darren. 240 minutes for X, 30 minutes for Y. So these are going to be the points on our scatter plot. First point, second point, third point, fourth point, fifth point, sixth point, and seventh point. Well, we have a total of 7 objects. So that is how you would map those. And here's what we have. 7 points are here. The first one has 30 minutes and 180 minutes. So 30 is here for this point and 180 is here for this point. 30, 180. That's the first one. Then we have second, third, fourth, fifth, sixth, and seventh, as we have numbered them over here. Okay, so there appears to be a relationship between the time spent on homework and the time spent watching TV. It is linear as they move. If we draw a straight line, the points can be fitted around the line, and it appears to be decreasing, that is, they're going downwards. So there is a negative correlation. This means students that watch more TV spend less time doing their homework. That's what it means. Let's look at a popular machine learning dataset called the Iris dataset. This is a database of flowers that look like this. This one is called an Iris virginica. which is kind of like a purple flower with longer petals. And then we have an iris setosa, which is more like a pink flower with more of a round petals. If we look at our previous PowerPoint, we can see an example of those. Oh, let me make sure that I didn't confuse them. So the iris setosa will be the one with more of a round petals, while the iris virginica, which is what we have here as well, will have an elongated petals. Okay, this one has more of a round circular petals. This one has more of an elongated petals. So this is a different class of flower. The one with the round petals is called setosa, and the one with the longer petals, virginica. So what do we want to see here? If we are to create a scatter plot for these flowers, there is 3 classes of them actually. There is setosa, virginica, and versicolor. If we are to plot them based on the size of their petals, their width and their length, we can clearly see here they are 3 groups of flowers. These setosa flowers are shown with squares. They are down here to the left. The versicolor are shown with circles, and they are in the middle. And then the virginica are shown with diamonds, and those are on the top right. The virginica would have the biggest length and the biggest width. This means they are round flowers, and overall their leaves are bigger than the others, than the other classes. The smallest one will be the setosa. It will have a smaller length petals, elongated, smaller width and smaller length altogether. That's that one right here. Wait a minute, the setosa. Yeah, that's the setosa. Okay, so if we are to plot these in space, this is what they look like. Discretization is something that would allow us to, if we have way too many values, that makes it difficult for us to determine the class, whether it's setosa or virginica. We want to know this. What's the class of the flower? If we're building a classifier such as the decision tree that we have seen earlier, or a rule-based classifier that's going to tell us, hey, if your petals are of size 1 and 2, then you've got an iris setosa. These are the ones over here. If your petals are of size 6 and 7, then you've got an iris virginica. These are the ones over here. In order to make this kind of decisional prediction, what is the class of the flower, correctly, accurately, we need to have a specific number of values for those petals and for those attributes. If we have way too many values, it can make it difficult for the machine to learn what makes the flower to be virginica and what makes it to be a setosa. So we want to, if we have way too many values, let's say we have infinite number of values between 6 and 7. Each single flower has a different number. One is a 6.1, one is a 6.2, one is a 6.3, one is a 6.4, one is a 6.6, one is a 6.7, one is a 6.8, one is a 6.9, and the next one is a 7. Each one of those get a different number. That will make it very difficult for the machine to learn what is an iris, makes it to be an iris virginica, because each of those has a different number. The machine needs to see a couple of examples with a repeating number in order to learn to have a sufficient number of examples in order to learn to build a model classifier, like a decision tree, a rule-based classifier, a neural network, or anything like that. It needs to have a sufficient number of examples with a repeating value. So if we have got all those differing values, in order to improve the learning of the machine, we and the building of the models so that they're accurate, we can do discretization. Discretization means mapping infinite number of values, let's say from the real world, from analog signals, into a discrete form. This means finite number of values that is easy to differentiate between them, to have sufficient repeating examples, and to store them in the computer. Because if we have infinite number of values, there is no way we can store them in a computer memory, because we don't have infinite computer memory. That's why you've got those digital pictures, discretization or digitization is the same thing. If we're to take a picture with an analog camera that will take the picture on a film and print it out into a paper, guess what? That picture has infinite number of colors or pixels on it. If I want to save this picture in a computer memory, we have to break it down into pixels and say, I'm going to record 512 pixels on the x-axis and 512 pixels on the y-axis. So the picture is of resolution 512 by 512, or it can be 512 by 1024. But we have to choose. We have to choose how many pixels we're going to store, because we can't store infinite amount of pixels. So the process of taking the infinite amount of pixels and converting them to a finite number of pixels so that we can store it in the computer is called discretization. So if we got too many values for the petals of the iris virginica, we can do discretization. This means we're going to map some of those into an interval. Let's say we are gonna have two numbers here between 6 and 7. 6.5 and 7. That's it. All the ones that are between 6 and 6.5 will end up into the first number, and all the ones from 6.5 to 7 will end up into the second number. So we're going to have two intervals and only two values. We're going to convert these differing values for every single flower into two exact values. So that will improve the learning of our machine and the accuracy of our classifier. So we can do this kind of discretization. And we will find, if we do this kind of discretization, that the data consists of 4 groups or points. There are 2 outliers. One is over here and one is over here. Okay. So once the discretization is done, we can do the linear modeling that we have seen earlier, or we can that can assist us to choose our intervals. So as I mentioned earlier, I wanted to have only 2 intervals for the iris virginica to make the accurate prediction, because I have seen that I had too many values for each flower had different values there for the petal. Here we are suggested to take 3 intervals with equal width in between them for mapping the attribute values into a specific interval. So, like we said, that's going to help us to determine the class of the flower and to have a more accurate classifier. Okay, so that is all that we have today for scatter plots and interpreting the scatter plots.